recording this. Okay, so here's the situation. We have a 100-kilogram boy on the top of a slope that's 20 meters high, and he's not having any initial velocity, and now he's got a certain amount of potential energy, and I work it out as 19600. 19600, and it's in joules, a scalar quantity. Now we call the sum, we call potential energy, it's part of the family of mechanical energy. Potential energy and kinetic energy add up to mechanical energy. And there's a law that says mechanical energy is conserved. So now, if he's at the top of the hill and he goes down the hill, he can go over bumps, over bumps, over bumps, and then he can go and rise. Excuse me. He can rise till he gets back to the same height on the other hill. So let's say this is position A. This is position B. This is position C. And that is position D. Okay, what you've got to know is that at every single position, his mechanical energy, his sum of potential and kinetic is always the same. So if at the top of the hill he has 19600 joules, then I would ask you, at the bottom of the hill, how much has he got? Bearing in mind the law of conservation of energy, of mechanical energy. Well, the answer is 19600 would be. And if I asked you what was his energy at C, he's going over all these bumps, there's no friction, then he's going to have 19600 joules. And then when he rises up the hill, you'll get to D, and he'll still have 19600 joules, because energy is mechanical energy under the force of gravity, which is a conservative force, we call it. None of the energy is lost. Okay, so that's the first thing that is, I mean, how easy is that? Energy, there, X is equal to X is equal to X is equal to X. Always the same amount of energy, mechanical energy is conserved. Now, does the path matter? Well, that's what we call a conservative force or conservative energy. E, non-conservative is the opposite of work, non-conservative. A conservative force like gravity, it doesn't matter what path you go, the energy will still remain the same. But now we introduce friction. So this is why I say physics is harder than maths. You see, this is the ideal world. This is like the mathematical world. In the mathematical world, you make your own rules, right? But in the real world, there's ugly, horrible things like friction, which slows things down. So let's suppose there was friction. So our skier comes down. Let's say there's no friction, no friction, no friction, no friction. And then suddenly at the bottom of the hill, he encounters friction. And let's suppose that he only rises to 15 meters on the other side of the hill. Well, if you think about it logically, he lost that amount of potential energy. Where did he lose it to? He must have lost it to friction. So he lost that amount of energy to friction. Where else could he have lost it to? There's another law that says, the law of conservation of energy, not just mechanical energy. It says energy cannot be created or destroyed. It can only change from one form to another. So here it was first potential energy, then it turned to speed energy or kinetic energy at the bottom. Kinetic, 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 kinetic. Then it turned back to potential, but it also turned back to a little bit of friction. And what does friction always do? Rub your hands together. It creates heat. So where did this amount of energy go to? It went into heat. Okay, so we lost that amount of mechanical energy. But I thought you said, sir, that mechanical energy is conserved. Yes, when there is no friction. So you've got to learn two situations. One where there's no friction, one where there is friction. So the next question we can ask ourselves is, if he lost 5 meters worth of energy from the 20, then how much energy went into friction? Well, think about it logically. 5 meters is 1/4 of the slope, so I could quarter that. Or I could say EP lost equals this MGH equals MGH equals 100 times 9,8 times 5 meters. And so if I work that out, I bet the answer will be 1/4 of that. 100 times 9.8 times 5 equals, I get 4,900, which I'm just going to say times 4 gives me back to 19600, which is exactly what I predicted. So potential energy lost was 4,900 joules, or we lost 5 meters of the Hill's potential energy and it went into friction. Now in the exam, you've got to explain how you do things to the examiner, right? So in the exam, what I've just done now, this quick and dirty method, would not be acceptable. The way you do it is you go to a formula. And here is the formula you want. It is in your BFF, or best physics friend. And it is this: work non-conserved. In other words, work, always when you see NC, it means friction. Work done by friction equals change of kinetic energy plus change of potential energy. So now you must preferably work it out with that formula. So I'm going to, where can I work it out? Let me just try and work it out here below. Okay, so let's use this formula here. If you don't mind just writing this down and doing it with me. Work non-conserved. In other words, this bit of the hill is equal to change of kinetic energy plus change of potential energy. So this is how you do it in the exam. Now, change of anything is K final minus K initial plus change of potential is U final minus U initial. Put them in brackets, they're two separate things. Doesn't matter, but let's do it in brackets. Okay, hope you can all see that. Okay, so now what was his initial kinetic, what was his final kinetic energy? Now, kinetic energy is half mv squared. He started with no energy of movement, he ends with no energy of movement. But write the whole formula, half mv v final squared minus, okay, I'm just gonna have to get rid of this, minus a half mass times v initial squared plus, what was his potential energy final? We always measure it, he was at 15 meters from the ground, from naught. So it's going to be his mgh final minus his mgh initial minus his mgh initial. Okay, so we know that he started with no energy and he ended with no kinetic energy. I'm leaving out a step here, but you would actually put in half m v naught v naught. Don't leave out steps. Don't be lazy like me. Okay, but you know how you would fill in that. Plus, what's his mass? 100 times 9,8 times, what was his final height? 15 minus, what's his mass? He hasn't changed mass, getting down to the bottom, he's still 100, times 9,8, that hasn't changed, times, what's his height initial? It was 20. And then you're going to come to your answer, which is 1960. I mean, okay, let's just do it. 100 times 9.8 times 15 equals 1470 minus 100 times 9.8 times 20, which was our 19600. And then the difference between the two is exactly what our friction we worked out before, minus 147004900. But it's a minus 4900. Okay, so the object lost due to friction. The object lost due to friction 4900 joules on this section of the hill. I see that we have lost our folks. So I'm just going to continue, and then when they come back, we'll continue. Okay. So now we know on that part of the hill, but this is the way that you would work it out. You would use that formula, work non-conserved or frictional energy lost is change of kinetic plus change of potential, and then you end up with a negative quantity. In other words, the friction is always like a negative force. It's always opposing motion, and therefore the work that it does by friction is always a negative amount of work. It sucks that energy. That object loses that amount of energy, and that goes into your friction. Okay, so that is how you would solve that problem. Now, the other formula that we've got to be very familiar with is this formula. Work net is change of kinetic energy. Work net is change of kinetic energy. That is called the work-energy theorem. This is the work-energy theorem. If you do work on an object, you change its kinetic energy. So if you do work on an object, you change its kinetic energy. Now, how do you do work on an object? Well, you can have gravity pull on it, you can have friction pull on it. So normally work net is a sum of all the gravitational forces and the frictional forces. And so you must be familiar with that equation as well. As I say, I'm going to just continue, even though I know I lost you guys, but let me just go on with a new problem, because I'm recording this. And I want to show you how the work-energy theorem is normally used. Okay, so let's work in this piece of board. I don't want to rub everything out in case the folks come back. So the work-energy theorem is this formula. Work net equals change of kinetic energy. I like the K because EK is also fine, but EK has one more letter. And if you're lazy, like most physicists are, you don't want to write that extra letter. So choose one. If you want to write EK, you can write EK. Okay, so let's just see if anybody's coming back. I don't see anybody here. So let me give you an example of where we use the work-energy theorem. Let's suppose we have an object, and here we have a pulley. Here's a weight. Let's suppose this surface has got frictional force. So there is friction. And let's suppose the friction is going to be 100, let's make it 200 newtons, frictional force. And let's suppose, I don't know if that will work, and let's suppose this mass is 10 kilograms. And let's suppose the angle of the hill is 20 degrees. Okay. So, yay, you're back. Okay, so maybe someone could just type, you can see me again. I think you're back. But we'll trust that you are back. I just want to show you what I did while you were gone. We worked out work done by our NC non-conservative force was our work done by our non-conservative force was our kinetic energy plus our potential energy changes. Okay, so there was no kinetic energy. We started not moving, we ended not moving, so both were naught minus naught. We finished at a lower down on the hill, we ended high, we started, there's the initial. High on the hill, there's the final, lower on the hill, and we worked out by this method, which is the preferred method, using a formula, we worked out our work done by the non-conservative force of friction, and it ended up as a negative number, as frictional work always does do. Okay, so if you missed some of this, I'm definitely putting the video back, but I've just gone over what you missed. So there I worked out the same answer as you had before. So then I went on to what is called the work-energy theorem. Okay, this formula is the work-energy theorem. And it states that the net work done on an object is equal to the change of kinetic energy. It's on your BFF. Okay, so I wanted to give you a problem which has got, I wanted to give you a problem how we use the work-energy theorem. And I didn't want to rub that out yet, just so that you could see what I did. Okay, so here would be a classical work-energy theorem kind of problem. Let's suppose we have an object moving at a constant velocity up a 20-degree slope. It's got a friction of, let's make it 20 newtons. I wonder, it would have a tension in the string. Maybe that's what we've got to work out. Find the tension in the string. But that would be the sort of problem that they, or maybe they would give you the tension in the string and then ask you to work out the friction. So what you have to do is work out the force times distance that these things are working, that these things are going, etc. You know what, I think I prefer to do this when I can see you. So I'm just saying this would be the type of problem that they would use the work-energy theorem. You'd say your change of kinetic energy, it's moving at the same speed, and then you're going to use the force times distance. You're going to use all the forces acting on this to work out its change of kinetic energy. I'll get a real problem for you to show you. Okay, but what I think I'm going to do now is let's go to let us go to your paper 1. So I'm going to just go there to the paper 1 question book, your multiple choice question book. And before I do this, I just want to go to share screen. And let's just see if I can find, okay, let's just go here, share. Okay, so there is a pendulum. So at this position here, the pendulum has only got potential energy. And at that position at the top there, it's only got potential energy. But at the bottom, it's only got kinetic energy, got no potential energy. And a pendulum is a perfect example of changing potential, kinetic potential, kinetic potential, kinetic potential, kinetic potential, kinetic potential. So it keeps on changing its mechanical energy, but the mechanical energy stays the same. This pendulum would go on forever. I just want to show you, just while we're here, a movable double pendulum. Okay, so you don't have to have just a single pendulum bob. You can do this with a pendulum. Now watch that. There it's changing kinetic into potential energy, but it's two objects, two parts of the pendulum doing it. And you can actually make one of these, and it creates some very interesting kinds of movement. Just watch that. There is now, it's performed a different sort of movement. But it's, so you'll see at times it's got a lot of kinetic energy, and at times it stands still. It's turned all its energy into potential energy. So this site, what is it called? It's called myphysicslab.com. Okay, myphysicslab.com. And so you can see there's another example. I just want to see one last one here. I hope you can see it. Newton's cradle. Okay, Newton's cradle is another example. There, potential energy, and then it changes it into, this ball gets kinetic energy. So we're actually using two laws of conservation. From here to here is the law of conservation of mechanical energy. Then we've got the conservation of momentum principle applying. And then we go back to the last ball gives this ball mechanical energy again. And so then it changes, this last changes into kinetic energy, potential kinetic, kinetic potential, and so on. So these are all examples of conservation of momentum. Okay, so now let's go to your booklets. Just hope that this thing's still working. Otherwise, I've got a problem, haven't I? Just let's see if I can get this to refresh. It's supposed to have my paper 1 booklet on it. But I think what happens is it's loading the PDF. Okay, there's the document again. And it's going to be a bit slow because it's going to take its time to load all these pages. So let's just try and move it up. Okay, but it's got to reload them, so it's going to take a bit of a while. We want to get to page 5 or 6, which has got our formulae on. Come on, move up. There's momentum formulae. Projectile motion formulae, page 6. Come on, go up. Okay, so here we're back onto our energy formulae. I just want to check. I hope that you guys can see this and that it's doing it. So I presume that you're still able to see this, but I've lost my Zoom page. But anyway, I'm going to have to just stay here. Okay, we're going to do problems in a moment, but here is your work done by a constant force is defined as a scalar quantity. It's the product of the force times the distance. That's a very important formula there. Okay. Remember that formula. Then there's your kinetic energy formula. There is your potential energy formula. Here, this is a formula not on your data sheet that's got mechanical energy is the sum of kinetic and potential energy. Here's your power formula. This formula, power average, is force times velocity average. We don't really bother with that much. I've never seen that come up in the exam. And then here's your work-energy theorem. Okay, work-energy theorem. This used to be hugely important. Okay, just want to make sure that I am there. Okay, I'm just going to share screen again, just in case, to make sure that you guys can see this. I suspect this year there's something that bothers me, that they're not going to focus as much on the work-energy theorem, but we need to know it. Okay, so the work done by the resultant or net force acting on an object is equal to the change in the kinetic energy of the object. That is summed up by that formula, work net equals change in EK. And honestly, you've got to learn that. The work-energy theorem is really supposedly the heart of this section. But you know, what bothers me is the questions we're going to do in a moment don't use this formula hardly at all. So why this year do they not tend to show that? Okay, I just want to go down to page, I think it's 22 is the first problem. Okay, on yours, it's page 10. Let's just see, I think that was the page I wanted. Oh yeah. Okay, 1.15. The speed of a bicycle increases from 2 meters to 5 meters per second. Its kinetic energy increases by a factor of how much? So how much is its kinetic energy increasing by? As I say, I hope that you're still there because something seems to be happening with Zoom. Okay, so let's just go to page 16. There's the page 10, there you see the question. Okay, so let me see if I can get something that I can write with here more. Okay, let's draw. Okay, so what is the formula for kinetic energy? Okay, let's try text first. Kinetic energy, capital K, equals 1/2 mv squared. Yeah, I'm not going to get superscripts. Okay, equals 1/2 mv squared. So you say, you say case 1, K, let's call it 1, equals 1/2 m1v1 squared. Okay, so a bicycle increases from 2 to 8. So case 1 is going to be that when it's at 2 meters per second. So this is how you do it. You say, okay, so let's just say case 1, kinetic energy 1 is going to be 1/2 times, we can choose any mass we want. Okay, let's say mass equals 2. And let's say, well, we know what its velocity. Velocity 1 was equal to, its initial velocity, you could say, would have been better than velocity 1. No, I would say still use velocity 1 is going to be equal to 2. So here we're looking at when it's 2 meters per second. So let's work it out, okay? So if we have it going at 2, what is its what is its kinetic energy? Okay, so we're going to do it. It's a little awkward working with this disk. So it's going to be, again, 0.5 or half times mass of 2 times 2 times 2 squared, which is times 2. And that 2 times 2 is 4 times 2 is 8 divided by 5 is going to be, it's going to be equal to 4. Okay, so we got a half times mass of 2 times velocity squared, and that's going to be 2 times 2 is 4 times 2 is 8 divided by a half is going to be 4, and that's going to be joules. Okay, so when it's going in, at case 1, that's how much energy, kinetic energy it's got. Now let's look at case 2. Case 2, K2, which is case 2, is going to be equal to a half times, it's the same, the mass hasn't changed, it's still the same mass, so we can say M1 times V1, but it is changed to 8. So it's going to be 4V1. 4 times the initial velocity squared. Oops. Squared. So it's going to be times 4 V1. That's 4V1 squared. Okay, so that is what you do. You state case 2 in terms of the same things as you had in V1. So now we're going to write, let's work it out. It's going to be equal to 0.5 half times, the mass is still 2, times 4 times 4 times 4 times 4 V1. And that comes to, let's reach for the trusty old calculator. Okay, so that's going to be 0.5 times 2 times 4 times 4, 16. It's going to be 116 times V1. And therefore, its kinetic energy has increased from 4 joules to 16. So it's increased, it seems to me, by a factor of 4. Now, when I worked it out before, I just want to look at it and see that I've done nothing wrong here. I got a different answer. Just let me, whoops. Just let me check something here. Where is our drawing? I think where is our drawing too? Okay, so I just want to check it out here. Okay, so that we've done nothing wrong. We state our case 1. Kinetic energy 1 is half M1 V1 squared, where M1 is 2 and V1 is 2. So we work it all out, half times 2. I chose 2 to cancel out the half, so those cancel out. So then our amount of energy is 2 times 2 equals 4 joules. Okay, now case 2 is got to be stated in terms of case 1. A half times 2 cancels out. And then this one was 4 times 4 was 4 times V1. Right, here's the problem. It's going to be equal to, instead of putting 2 here, I've got to put 8 here. Because what is its velocity? It's 8 times 8 times, or it's 4 times. I'm getting myself confused here. I got that as the answer when I worked it out. But if you just put in 8 there, and 8, and you get 64, and sorry, for a moment, I'm a little bit confused here. Which do we use, 8 or 4? Is it 4 times 4v1, or do we put the 8? Let me think about it. Sorry. It's either that answer or that answer there. But half mv. Yeah. Okay, so this is actually the way that you would resolve it. You would say, in this case, you just put in pure numbers. Mass, half times mass times pure velocity is 2 times 2, that's 4. In here, this case, you just put in the pure numbers. A half times 2, put in the 8 times 8. Okay, let's just work that out. So it's a half times 2 cancels out, that's 1. 4, 4. I mean, 8 times 8 is 8 times 8 equals 64. Okay, so in the second case, when it's moving at 8 meters per second, it's got 64 joules of energy. So how does 4 compare with 64? Well, then you divide the 4, which was its original energy, by the 64. So I'd say 64 divided by 4 equals 16, and therefore that must be the answer. Okay, so where did I confuse myself? But you do it like this. You do the second case, the mass hasn't changed, the velocity has changed. Type in the velocity in the second case. Then you get your kinetic energy in the second case was equal to 64. How does 4 compare with 64? It increases by a factor of 16 times 4, 16 times. Okay, which is quite surprising because if its speed has only gone up a little bit. Okay, let's find the next work-energy theorem problem, or anything to do with work and energy. This is getting to be a bit slow, but let's just carry on. What are we on? We're on page 13 now. I don't see any related to this section here. Let's just carry on. Okay, yeah, looks like something. 1.25. An object moving horizontally at a constant velocity suddenly encounters a rough horizontal surface. The object continues to move over this rough surface. Which one of the following statements is correct? Now, the net work done on the object during the motion over the rough surface, is it 0? Is it positive? Is it negative? Or is it constant? Okay, so what you've got to do is you've got to look at your BFF. And what does it say? An object moving horizontally at a constant velocity suddenly encounters a rough surface. The object continues to move over this rough surface. Which one of the following statements is correct? Now, what do you think is going to happen to it when it encounters the rough surface? It's just going to slow down. And so, the net work net is equal to a change in kinetic energy. And its kinetic energy is going to get less. So therefore, you've got to go to your work-energy theorem. Work net equals a change of kinetic energy. Okay, so you're going to use this formula. Work net equals delta, or change of kinetic energy. And so its kinetic energy is going to change. It's going to get slower. Therefore, it's going to, like we saw, it's going to have a negative. And so I would say the answer to 1.25 is going to be C. It's going to have negative work done to it. Okay, so 1.25, the answer is going to be C. Why? Because its kinetic energy is going to change when it hits friction. Let's look for some more questions that are related to this section. That is not strictly related. That's not strictly work-energy theorem. It's not work-energy power. We should be getting to something soon. Work and time, okay. The graph below represents the relationship between the work done on an object and the time taken for the work to be done. So there's work, there's time. Now the gradient of the graph represents, now what does the gradient of any graph represent? You take your vertical divided by your horizontal. And what is work done divided by time? Power. So the gradient of the graph is power. I don't even have to look further. Okay, so the answer to 1.35 is power. I hope you see the reason why. Gradient of a graph, your y-axis over your x-axis, and work done over time is power. Now, when you guys can do these problems, like almost unthinkingly, then when you get them in the exam, then you're going to really, man, you're going to sit in this exam, you're going to be so happy. Let me tell you, you're going to be so happy when you see these problems that you've seen before. Okay. Yeah. 1.45. The work done by a consistent force applied to an object to increase the object speed from v to 2v is w. The work done by the same force to increase the speed of the object from 0 to v will be. This problem is actually quite hard. I'll tell you why. In this case, you've got three cases. You've got, whoops, let's just get text. Okay, you've got case one, when the velocity is equal to 0. Then you've got case two, where the velocity is equal to v. And then you got case three, where the velocity is equal to 3v, 2v. So here it says the work done by a constant, whoops, the work done, let's just get back to goal, by a constant force F applied to the object to increase the object speed from v to 2v is w. So to go from v to 2v, the work was w. That should have been a v. Now the work done by the same force to increase the speed of the object from 0 to v will be what? Okay, so this is how you're going to do it. You're going to again go to your formula for kinetic energy. Okay, and your kinetic energy formula is equal to a half times m times v squared. Okay, that's your kinetic energy formula. Now, what you've got to do is, in case one, now make your mass 2. So then the half and the 2 cancel each other out. Now, start playing with your numbers here. Okay, so what is going to be the case when your velocity is 0? Okay, so let's take that, let's substitute that in. 0.5 half times, let's say the mass is 2, just to cancel out the half. times naught squared. And so that answer is going to be naught times naught. So there you're going to find that the kinetic energy is going to be equal to naught because it's not moving. Okay. So now let's go to case 2. There, case 2, we got half. Again, we write the formula. Case 2 is equal to 0.5 times, the mass hasn't changed, times 2 times V. Equals, so what is 0.5 times 2? That's going to be 1. And our velocity is just going to be equal to V, which is going to be V squared. Sorry, V squared. Let's just go back here. It's going to be half times V squared times V. And so our answer is going to be V squared. Now, what I suggest you do here is just give V a number. Okay, so let's say that V is 1. So it went from 0 to 1 to 2V, which is 2 times 1, which is 2. So let's just give it a real number. Okay, so let's say V initial, the object's initial speed was, just say 1. Choose an easy number. So it's 1 times 1. So what is that going to be the answer be? So half times 2, that cancels out, times 1 times 1, and then the answer is going to be 1 joule. So it went from 0 to 1 joule. Okay, so that was your second case. Now let's go to our case 3. Case 3 is, again, you write your formula and then you say 0.5 times 2. Those are going to cancel each other out. That's why I chose the mass of 2. Times, now the velocity went up. It said it doubled. It went to 2V. So if the initial was 1, it's going to be 2 times 2. So 2V is 2 times 1 is 2 times 2. So what is that going to be equal to? Those two cancel. So it's going to be 4. Okay. So look at that. Your initial energy at 0 was 0. Your next energy at V was 1. And your energy at 2V was 4. So now let's see if we can answer this question. The work done by a constant force applied to the object to increase the object's speed from V to V was W. So to go from 1 to 4 was W. So to go from 0 to 1, 1 minus 0 is 1. 4 minus 1 is 3. So it's 1 lot versus 3 lots of energy. Look, 4 joules minus 1 joule. Here the difference was 3 joules. Here the difference is 1 joule. So here it's going to be a third of W. So the answer has to be A. So that was 145. Okay, that was a difficult question. But I want you to see the way we do it. Okay, same way we do all of these problems. And I really believe this year they're going to give us a question like this. I don't think it's going to be a big question or a small question. But do you see what you did? You read the question. You see it had going a case when it was going at a velocity V, 2V, and 0. So there were the 3 cases. Choose easy numbers, plug the numbers in, turn the handle, get values for your energy, 0, 1, 4. And then if the change from here to here was W, and W is equal to 3, then the change from here to here was a third of W, and there's how we got our answer. Pretty tough question, I will grant you that. But you know what? When you've seen those questions a few times, you get better at doing them. And hopefully when you see that question again, it won't bother you. Okay, now let's find another work problem. Okay, here's 1.55. When the net work done on an object is positive or greater than 0. Okay, look, what I know is friction is negative work. So positive work must speed it up. Okay, friction, negative work, get used to that. Positive work must speed its kinetic energy up. So with that in mind, when the net work done on an object is positive, kinetic energy of the object is 0. No. Kinetic energy of the object is increasing. That looks good. Kinetic energy of the object is decreasing. No, that would be negative work. Kinetic remains the same. So the answer has to be this. It's getting faster. Positive work makes things go, increases the kinetic energy. Comes from, again, the Work-Energy Theorem. Net work equals change of kinetic energy. If the change of kinetic energy is positive, then the net work must be positive. So we're on page 29, nothing of interest, nothing to see here, folks. 30, nothing there. 31. That's a vertical projectile question. Okay, here 1.65. A block of mass M is released from rest from the top of a frictionless inclined plane QR. The total mechanical energy of the block is EQ at point Q and ER at point R. The kinetic energy of the block at points Q and R is KQ and KR. So the total mechanical energy is at the top is the total mechanical energy is EQ. Okay, which one of the following statements regarding the total mechanical energy and the kinetic energy of the blocks at points Q and R is correct? Okay, before I look at all that junk there, what do I know? I know the mechanical energy there and there is going to be the same. And I know the kinetic energy is going to increase as it goes down. So I'm looking for an answer which says mechanical energy is the same and kinetic energy is increasing. Okay, so I'm looking for one of the answers with equals. The mechanical energy at Q and R are the same. So it's either B or C. Now, let's have a look at here. I want KR must be greater. KR is greater than KQ, and that's the answer there. KR, kinetic energy at R, is greater than KQ, or KQ is less than KR. So the answer's got to be B. Why? That is saying mechanical energy at Q and R, by the law of conservation of mechanical energy, it stays the same here, but I know that it gets faster down the slope, so the kinetic energy at point R must be greater than the kinetic energy at point Q. Okay, that. Although it's complicated looking, it was actually quite easy. You know, once you learn to read, I'm a bad reader. I'm a terrible reader. I make mistakes all the time because I don't read carefully. My mommy never taught me to read when I was young. So why don't we blame our parents? That's very popular. My son learned to read at age 2. Flashcards. He's a brilliant reader. Okay, 1.74. When the velocity of a moving object is doubled, the net work done by the object is doubled. The kinetic energy of the object is doubled. Potential energy of the object is doubled. Linear momentum of the object is doubled. Okay. Now again, you're going to go to that formula. Kinetic energy equals 1/2 times m times v times v, half mv squared. Okay. So what you got to know is whenever velocity increases, it's exponential. It goes v times v. So let's have a look here. When the velocity of an object is doubled, the network is not doubled. It's when the velocity goes from 1 to 2, it's 2 times 2, it becomes 4 times more. So it's not, the network is not doubled, it's 4 times more. The kinetic energy, no, it's also 4 times more. The potential energy doesn't change. And the linear momentum, yeah, that's momentum is mass times velocity. So here we're going to say P equals mv. So if you double the velocity here, you double the momentum. So that must be the answer. Okay, so do you see this is the one that would double? But because it's a squared function, if you double the velocity, you 4 times, 2 times 2, you quadruple the network and the kinetic energy. So that's why the only thing that doubles here is the linear momentum, which is mass times velocity. Okay, here's another one. The network required to stop a moving object is equal to inertia of the object, change in kinetic energy of the object, change in momentum of the object, change in impulse of the object. Okay, what again formula have you got for work net? Work net is change of kinetic energy, work-energy theorem. It's just another way of stating your work-energy theorem. Must be that. There's no network formula in momentum. You can't find a formula, and you can't find inertia as part of momentum section, so it has to be B. Okay, that's Doppler and a few other things. Circuits, photoelectric effect. Okay, let's see if we can find some work-energy theorem problem here. Must be on the next page, hopefully. Okay, a ball moving horizontally hits a wall with a speed of 2v. The wall then bounces back horizontally with a speed of v, as shown in the diagram below. There's your 2v, there's your v. Which one of the following combinations regarding the linear momentum and the total kinetic energy of the ball for the collision above is correct? Assume that the ball wall system is isolated. Okay, so look, if its momentum, if its velocity changes from 2v to v, remember we learned from the past that 2v's got 4 times the energy of v. So let's look and see. Which one of the following combinations regarding the linear momentum there, okay, is momentum conserved? Is the total kinetic energy conserved? Okay, so its kinetic energy is not conserved. So is the linear momentum conserved if the ball bounces off at half the velocity? Well, what is the law? In any collision, momentum before equals momentum afterwards. So what happened is, during the collision, actually the wall gets a bit of momentum that way, and the ball gets some momentum this way. So, but the total momentum, if you added the ball and the wall, some tiny bit of momentum the wall gets, the momentum is conserved. So linear momentum is always conserved, but the total kinetic energy is not conserved. So it has to be A. Momentum is conserved because your system includes the wall, earth, and the ball. That whole thing is your system. And any momentum lost by the ball is gained by the wall. But the momentum stays the same. That's the law of conservation of momentum. It's quite a tricky problem. But now that you've seen it, okay, let's go to which one of the, no, we're not doing that. Which one of the following energy conversions take place on an AC generator? No, we're not doing that. We're looking for energy problems. Okay. No, that's not work energy problems. We're on page 44. That's vertical projectile motion. Okay, let's just see if this is an energy problem. A trolley of mass m is moving v to a frictionless horizontal ball of clay. No, that's a momentum problem. Okay, yeah, it looks like a work problem. A person lifts a crane vertically upwards at a constant velocity through a distance h. The person does work x on the crate in time t. The person now lifts the same crate vertically upwards at a constant velocity through the same distance but in time 2t. The work done by the person on the crate will now be, okay, so this is lifting a weight up from there up to there. And we know the formula for that is going to be, it's gaining potential energy. So it's going to be mgh. Okay, so if I had to look for a formula for this, I'd say potential energy, or EP, equals mgh. Now, if you look at this, he's lifting the same crate through the same height at the same at a constant velocity. It doesn't matter. His mass hasn't changed, G hasn't changed, H hasn't changed, the potential energy hasn't changed, and that's the work done by the person on the crate. So the hasn't done any different amount of work, he's just got it done it in a different power. So if the first work was X, it's still X. He's still doing the same amount. If they ask him what was the power, it'll be half the power because he does it in 2 times the time. But they're asking the work, and work is mgh. Because the only work done, there's no kinetic energy change. So this is going to be just the same amount of work, it's gained the same mgh. Okay, so I hope you see why that is. These are all from past question papers. So do you see that I don't see too much of the work-energy theorem? And that's worrying me. I'm really certain they're going to give us something that's got this, it's going to play around with v squared. A constant horizontal force F is applied to a box on a frictionless surface. Okay, let's just have a look at this one. Constant horizontal force F is applied to a box resting on a horizontal frictionless surface. Which one of the following statements regarding force is correct? The force will cause the box to move with constant acceleration, constant velocity, constant kinetic energy, constant momentum. Okay, so this is actually Newton 2, but it's got a little bit of kinetic energy in it. Okay, we know from Newton 2 that force net equals mass times acceleration. So therefore, a force will cause an acceleration. So that has to be the answer. And a constant force causes a constant acceleration. Doesn't produce a constant velocity because the velocity increases, the kinetic energy increases, and the momentum increases. So it has to be A. But it's not really an energy problem. It's, I don't know, it's more a Newton problem. Okay, this is quite a cute problem. A pendulum bob is released from point B. This is like Newton's cradle. Above a horizontal surface. At the lowest point Q of its swing, it collides with a stationary block situated on a frictionless horizontal surface, as shown below. Ignore air friction. Okay, so here's the pendulum bob. We know that in all this part of it, it's the conservation of mechanical energy. Then we know when this hits that, it's the conservation of momentum that takes over. Okay, We know that when some object hits another, momentum is conserved. Momentum is always conserved. So the momentum at A here gets transferred to the momentum here. Which one of the following combinations of conservation laws can be used to calculate the speed of the bob at Q immediately before and after colliding? Okay, so at Q, I know that its speed is going to be calculated from the conservation of mechanical energy, not the conservation of momentum. This is conservation mechanical. So it's either A or C. Now, after the collision, there's going to be the conservation of linear momentum. So it must be A. I seem to always like A. C, we can't use the conservation of mechanical energy because this it gets changed from potential to kinetic. Here, it's momentum change that will determine the speed of the block after and the ball after. So yeah, this is our conservation of momentum rule. Q problem, okay, so the answer there was A. I hope all of you worked out your power. If you haven't worked out your power, can you perhaps go home and work it out? By doing press-ups or pull-ups, chin-ups. You see, this is not, let's see, this is more a Newton problem, but let's just have a go at it. The net or resultant force acting on an object is equal to, so this could be Newton 2, equal to the something of the object in the direction of the net force. The net resultant force is equal to the change in momentum, change in kinetic energy, rate of change in momentum, rate of change of kinetic energy. The net resultant force acting on an object is equal to the something of the object in the direction of the net force. So does force cause a change in momentum? Net force, change in momentum. So we're looking for a formula. I'm just trying to think. Force times time is change in momentum. The net force will cause a change in kinetic energy of the object. The rate of change of momentum, that would be the rate of change of kinetic energy. Well, rate of these two rates means divided by time. I'm just trying to see why force times time equals change in momentum. You know what? I'm going to have to think about this one. You're going to have to think about it too. A net, what does a net force do? It does change the momentum. It changes the kinetic energy. For the moment, I cannot, so this is question on page 53, 111. I cannot for the moment think of how we would differentiate and what the answer would be. Because a net force does result in a change in momentum. Yeah. Ft equals delta P, change in momentum. So force times time is a change in momentum. Change in kinetic energy. The question somehow eludes me, but I'm going to have to think about that. What they're getting at, and what formula we're going to use to solve it. Okay, here's 115. The net work done on an object to increase its speed from rest to V is W. How much net work must be done on the same object to increase its speed from V to 2V? Now remember, we did this problem before when we had a case of speed of 0, then a case of speed of V, which we said let it just be 1, and then 2V. And remember that to go from 0 to 1 meter per second cost a third of the amount of work. So to go from, now they're doing this problem kind of in reverse. The net work done on an object to increase its speed from From 0 to V is W. So from W to, so to go to 2V must be 3 times the work. That's just from remembering my past, when we worked out this problem before. So it's going to be 3 times the work. Why? Because it takes, go back and revise how we did that problem. It's going to take too much time to explain it. Okay. Okay, this is all electricity related. We're on page 57. Nothing of interest here, folks. We're now on page 58. Nothing on there. 59. Okay, let's just have a look. This looks like it could be an energy problem. Ball P and ball Q of the same mass are dropped onto a concrete floor. Both balls hit the concrete floor at the same speed, V. Remember, it doesn't matter what the mass of any object is, it will always fall at the same velocity and both will hit the floor at the same time. Both balls hit the concrete floor at the same speed, V. Ball P rebounds with the same vertical speed, V, but ball Q rebounds with half the velocity. Which one of the following statements regarding the collision of each ball with a concrete floor is correct? Kinetic energy is conserved? No, because this one is going at half the speed afterwards. The change in momentum of ball P is greater than that of ball Q. Okay, so if you go from 1 to -1, the change of momentum is going to be 2. You go from 1 to a half, it's going to be less. So it would be, let's suppose down was positive. It goes from final -1 minus +1 is going to be 2, and that's going to be less. So that looks correct. The contact with the floor is the same for both balls P and Q. We don't know, do we? Momentum is conserved for the collision of ball P, but not for that of ball Q. No, momentum's always conserved. So the change, this is a momentum problem. The change in momentum of ball P is greater than that of ball Q. Why? Again, if you want to, just take case 1, make its velocity when it hits the ground of 1, and then it rebounds at -1. So take down as positive. So what is change in momentum equals final, which is -1, minus initial, which is +1, it's going to be 2. Here it's going to be 1 minus half, minus half, and it's going to be, put that into a calculator, what it's going to be. Okay. If the network done on a moving object is positive, then we can conclude that the kinetic energy of the object is, remember, negative kinetic energy is friction that decreases its kinetic energy, so positive network is going to increase its, we conclude that the kinetic energy of the object has increased. B. We're on page 62 now. Let's look for a work-energy theorem. Okay, let's just have a look at 134. Ball M moving at speed v to the right collides with a stationary ball N on a smooth horizontal surface. Immediately after the collision, ball M comes to rest, and ball N moves to the right with a speed of v. Okay, that's like a Newton cradle. So it's like the Newton cradle when a ball hits it. Actually, you know that both balls are the same mass if this happens. Which one of the following statements about the collision of the balls is correct? So they comes in with a speed v, leaves with a speed v, a different ball. The total momentum is conserved and the masses of the balls are unequal. No, I know that the mass of the balls must be equal. Total kinetic energy is conserved. Yes, they both. And the mass of the balls are unequal. No. Total momentum and total kinetic energy are conserved and the mass of the balls are equal. There we go. See, you see with Newton's cradle, it wouldn't work if if your balls were at different masses. So when ball M hits it, the ball at the other side of the Newton's cradle leaves with the same velocity, and then it just keeps on recurring, tick, 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 tick. But it only occurs because the masses of the balls are equal. What's the general rule? If a small ball hits a big ball, the small ball bounces backwards, and the big ball just rolls a little bit in the direction of the original ball. If a big ball hits a little ball, both balls go in the direction that the big ball started in. And when one ball of the same mass hits another ball of the same mass, it's like in bowls or bowling or something. I'm talking about old babies bowling. If the balls are the same mass, then the first ball will, or like snooker, the first ball will hit the second ball, and then the second ball gets all the energy and goes off at the same speed as the first ball. I wonder why. It'd be interesting to think why in snooker or pool, sometimes the first ball carries on moving. Is it to do, what is it? Is it the way they hit each other? Okay, 135, you're going to hate this question, but I'm glad you're going to see it. Okay, a small stone is dropped from rest and undergoes free fall. Which one of the graphs below shows the correct relationship between the gravitational potential energy and the speed v and the kinetic energy k? So we've got potential energy, velocity, k. Okay, so this is energy versus velocity. As the potential energy decreases, as it falls, the kinetic energy increases, and it's exponential. Do k and u change linearly? Here, its potential energy changes slowly at first, then greatly afterwards, and its kinetic energy changes slowly at first and greatly afterwards, or is it linear, one linear and one exponential? Okay, look, if you drop a ball over time, this is how the ball looks. I've got the draw thing, yeah. The ball's there, then a second later, the ball's there, then it gets increasingly further away. That's exponential, folks. So at first, its potential energy difference hardly changes. So at the start of dropping it, its potential starts slowly, and it slowly builds up its kinetic. So C must be the correct answer. Here, its potential energy is great at first, and its kinetic energy change is great at first, and then, well, slow at first, then gets greater. But here, that's the correct shape, because slowly its potential energy, and then after a time, its potential energy is really changing as that. Look, the distance between the stones is getting greater, but that also means the kinetic energy is getting hugely greater. Nice question. If you'd like to read graphs. Yeah. Okay. Graphs are just stories. Daddy, tell me a story. Okay, have a look at this graph. Look at that graph, my son. What is a graph telling you? Telling you that the potential energy and kinetic energies are changing. Okay, which physical quantity is equal to the rate of change of momentum? Okay. So which physical quantity is equal to the rate of change of momentum? This is actually a momentum problem. But momentum is mass times velocity over time. So what's velocity divided by time? Going to be mass times force times distance. And that's net force times distance. Looks like that. But anyway, that's So rate of change of momentum is mass times velocity divided by time. So what is velocity divided by time is distance or displacement. So mass times velocity. So it's going to be mass times distance. Or is it impulse? Impulse is rate of change of momentum. What is impulse? I'm going to have to revise that. What is impulse? Impulse is equal to force times time. But impulse is also rate of change of momentum. I think it could be impulse. You're going to have to think about that. Good to know there's still a few things that are challenging that one has to think about, that otherwise it'd be very boring. But that's not a work energy problem. Okay, here's one. No. Come on. We're not at the end of this document, are we? Are we at the end of the document? Could be. 82. Yep. Okay, so we've done all the questions on work, energy, and power in this document. I think you guys may have left me long ago. Oh, well. We're just going to have to save this. End the meeting now.